Welcome to the video for tutorial 3. We are starting with exercises similar to the procedure exercises, and the first one we're looking at is under the exercises in section 7.1 of your textbook, and it's number 8. And it says the integral of t sec squared of 2t dt. Right, so section 7.1 is on integration by parts. So we're going to use integration by parts here. The first thing we're going to do is we are going to select our u and our v. So when we select our u and our v, we want to select u such that the derivative of u is going to make the integral that we get when applying the integration by parts formula easier. And we also want to make sure that what is left, which is going to be equal to v, is an integral that we can do. So a wise decision here would be to say, let u be equal to t, since then du just equals 1 multiplied by dt. So definitely we now have a simpler derivative. We had a t and now it's just a constant. And v is everything else that remains. So it's the integral of sec squared of 2t dt. We know that the integral of sec squared is tan, but we have sec squared of 2t, so it's going to be a half tan of 2t. So let's put it into our formula. So we know that our integration by parts formula is u multiplied by v minus the integral of v du. Right, so we have u, which is t, and we have v, which is a half tan 2t. So it's going to be a half t tan 2t minus, and then we have the integral of v. So I'm just going to write the half in front of the integral, and then we have the integral of tan 2t, and then we have du, which is just dt. Then we just rewrite our first term, and then we still have our half, and the integral of tan of something is equal to the ln of the absolute value of sec of that something. We just have to take into consideration here, we have tan of 2t. That means that the integral here is going to be a half, and then we have ln of the absolute value of sec 2t plus c. So this becomes a half t multiplied by tan 2t minus 1 over 4 ln of the absolute value of sec 2t plus c. If you were unsure about this half, how we got that, what you could do is you could just take this integral and do a substitution for it on the side on its own. So let's say we let w be equal to 2t, then dw equals 2 dt. So a half dw equals dt. So the integral will then be the integral of tan of w multiplied by a half dw. So we have a constant of a half, and then we have the integral of tan w, so it's just ln of the absolute value of sec of w, and then we just have to replace our sec of w with sec of 2t, so it's a half ln absolute value sec of 2t. Next is number 36. We are still busy with exercises from section 7.1, so we're still using integration by parts. So what we want to do now is, once again, we want to choose our u and choose our v. All right, so what we are going to do in this case is we can see that if we set u equal to either one of these functions here, so either e to the s or sin t minus s, the derivative of u will not become simpler. If we set it equal to e to the s, the derivative is just the same thing. If we set it equal to sin, the derivative is going to have a cos n. So in cases like this, what we usually try and do is we set u equal to something so that later on in the problem, we are going to get repetition. So what we are going to do here is we are going to set u equal to sin of t minus du is going to be cos of t minus s, but we are taking the derivative with respect to s, so it's multiplied by minus 1, because that's the derivative of minus s ds. So in other words, I have minus cos t minus s ds, and then v is the integral of everything that remains, so it's the integral of e to the s ds, which is just e to the s. All right, so let's put this into our integration by parts formula and see what we get. So we have u multiplied by v, so that's just going to be sin of t minus s multiplied by e to the s, and remember we have bounds here from 0 to t. Then we have minus the integral from 0 to t of v, which is e to the s, multiplied by du, which is minus cos of t minus s ds. All right, so what I'm going to do in the next step is I'm simply going to just rewrite my first term, and then I'm just going to take that minus out and I'm going to write it as plus the integral from 0 to t of e to the s cos of t minus s ds. Now we can see that the integral that we have here looks similar to the one that we started with, except we have a t minus s. So what we want to do now is we want to do another integration by parts, and we want to choose our u and v similarly as we did the first time, but this time we are going to set u equal to cos of t minus s. So what's going to happen is we are going to get a repetition because our derivative of u is going to be a sin. So in other words, I'm going to say, let's just call it u1 equals cos of t minus s. Then du is going to be minus sin of t minus s multiplied by a minus 1 ds. The minus 1 is just the derivative of the minus s. And then v, once again, is the integral of e to the s, which is just e to the s. And I can just write this as positive sin because we have a minus and a minus. So this is just going to become sin of t minus s ds. All right, so this means that this integral is going to be, sorry, I want to put a 1 and a 1 there, just so that we distinguish by the two integration by parts that we did. So this is going to be u1 multiplied by v1. So it's going to be e to the s, and then we have cos t minus s minus the integral, remember the bounds, from 0 to t of v1, which is e to the s, du1, which is sin t minus s ds. Right. So let's just write out the entire equation of what we have now. So I'm just going to start with this. I'm going to write that on the left-hand side, and I'm going to write what it's equal to on the right-hand side, everything that we have right now. So we started with the integral from 0 to t of e to the s sin of t minus s ds. And then we worked out our first term, sin of t minus s multiplied by e to the s. That's between 0 and t. And then we worked out our second integral, the one underlined in blue. And this is what we get. So I'm just going to fill in those values. So it's going to be plus e to the s cos t minus s minus the integral from 0 to t of e to the s sin of t minus s ds. As I said in the beginning, we were trying to get repetition. In other words, we were trying to get the same integral that we have on the left on the right, so that we can take that integral from the right to the left and add it there. And we do have that now. This integral is exactly the same as the one that we started with. So I'm going to take this one over to my left hand side, and I'm going to get 2 times that integral. So it's going to be 2 times the integral from 0 to t of e to the s t minus s ds equals, and then on the right hand side what I have is sin t minus s multiplied by e to the s plus e to the s cos of t minus s, and both of them are between the bounds 0 and t. Then in the next step, what I'm going to do is I'm just going to take this 2 over to the right and write it as a half multiplied by what we have in brackets. So the integral from 0 to t is e to the s t minus s ds. On the right I have a half, and then in the brackets I'm going to substitute in my bounds. So I'm going to have sin of t minus t, so it's sin of 0 multiplied by e to the t, plus then I have once again e to the t multiplied by cos of t minus t, which is just going to be cos of 0 as well. And then for when we substitute in our bottom bound, we have sin of t minus 0, so it's just going to be sin of t multiplied by e to the 0, plus then we have e to the 0 multiplied by cos of t. Right, so let's work that out. So we are going to have a half. Sin of 0 is 0, so our first term falls away. Then we have cos of 0, which is 1, so we have e to the t. Then we have sin of t multiplied by e to the 0. E to the 0 is just 1, so it's minus sin of t. And then we have e to the 0, which is 1 multiplied by cos of t. So it's minus cos of t. Next we are doing number 42. It says evaluate the integral by first making a substitution. We have the integral of arc sin of ln x over x dx. Remember, arc sin is the same as inverse sin. So we first want to make a substitution. Whenever we make a substitution, we want to make sure that whatever we use, let's just say this time we're going to use a y. I'm just going to use a y here instead of a u as usual, because later on I'm going to do integration by parts and I don't want to cause confusion with that u and v. So whatever I set y equal to, I want the derivative of that. So in other words, dy, I want that to be inside of my integral. So we also know that whatever we set y equal to is usually the inside of something. And here it's nice to see we have a ln x as the inside of arcsin, and the derivative of ln x is also inside of our integral because the derivative of ln x is 1 over x. So if we say y equals ln x, then dy equals 1 over x dx. So x dy equals dx. So if we write down what we get here, we get the integral of arcsin of y over x, and then we have x dy, and the x's cancel immediately. So we are simply left with the integral of arcsin of y dy. Next, we now want to solve the integral of arcsin. We don't immediately know that integral, so we need to use one of the methods that we have to find it. So the only method that we can basically use here is integration by parts, even though we don't have a clear product of two functions. We can't use any of the other methods. We've already used substitution. This is not a trigonometric integral. So definitely we are going to have to use integration by parts. So what I'm going to do is I'm simply going to say let u be equal to arcsin of y. Then du equals 1 over the square root of 1 minus y squared dy, since the derivative of arcsin or inverse sin is 1 over the square root of 1 minus y squared. And then v is everything else. So v is simply going to be the integral of dy. So it's just going to be y, right? So let's write that by using our formula for integration by parts. So we are going to have u multiplied by v. So it's y multiplied by arcsin y. Minus the integral of v, and v is just y, multiplied by du. So it's y over the square root of 1 minus y squared dy. Now, our integral that we have here is one that we can do by just using a simple substitution. So whenever you get a new integral, firstly check, do I immediately know the integral? If you don't, can I do this integral by using a simple substitution? If you can, do that. If you can't, try using integration by parts. But in this case, we can just do a simple substitution. So I'm just going to use a different letter again. I'm going to say for this integral, let w be equal to 1 minus y squared. Then dw equals minus 2y dy. So dw over minus 2y equals dy. So this means what we are going to get here is rewriting my first term, and then I have minus the integral of y over the square root of w, and then I have dw over minus 2y. The y's immediately cancel. So I have y multiplied by arcsin of y minus, and I have a minus and another minus there. So this is going to become plus the integral of w to the minus a half dw, which is y times arcsin of y plus, and the integral of w to the minus a half. Sorry, just quickly go back to the previous step. I just forgot one thing. We still have a 1 over 2 in here that we had to write in the front. So let's just put that in here. So it's 1 over 2. So now we have 1 over 2 w to 1 power higher. So it's minus a half plus 1 over a half. And then please remember to substitute back. So firstly, we know that w equals 1 minus y squared. So let's just quickly cancel those two halves. Then I have y multiplied by arc sin of y plus, then I have the square root of 1 minus y squared. But I'm not done substituting back, because in the beginning I said y equal to ln x. So I want to get my final answer in terms of x. So I replace all of my y's by ln x. So I have ln of x arc sin of ln x, and then I have the square root, so plus the square root of 1 minus ln x squared, and just don't forget your constant. The next exercise we're looking at is under section 7.2 and it's number 47. So section 7.2 is on trigonometric integrals. So we have the integral of 1 minus tan squared of x over sec squared of x. So this integral does not fit the form of the integral of sin to some exponent multiplied by cos of some exponent, and it's also not tan to some exponent multiplied by sec to some exponent. So what we are going to do is, when we don't have one of those forms, we are going to try and firstly simplify what we have, and we are going to do that by writing tan and sec in terms of sin and cos in this case. So this is going to be the integral. I'm just going to split it up into two fractions. So I have 1 over sec squared, and sec is 1 over cos. So it's 1 over cos squared of x, minus, then I have tan squared, which is sin squared of x over cos squared of x, and it's over 1 over cos squared of x. So this is going to become the integral of cos squared of x, and then minus sin squared of x dx. Alright, now try and use your double angle formulas, because you want to get rid of the squares, you want to get rid of the exponents basically in your trig functions. So this is easy. We can just immediately replace this by cos of 2x, since that's an identity. And the integral of cos of 2x is nice and simple. It's just 1 over 2 sin of 2x, and then plus c.